this lesson is the second derivative test. Now, we're working on the premise that you have already had the first derivative test. So this is the second derivative test. In the first derivative test, we tested critical numbers using the first derivative to determine whether or not they were a relative maximum or relative minimum. In this lesson, we're going to take the second derivative to test these critical numbers to see whether or not they are relative maximums or relative minimums. So we have after this, we will have two different tests, and they both have their merits, and we will explain that as we go along. The first derivative is the change in y over change in x, or as we have come to know, it is slope. Change in y over change in x. Now, the second derivative is the derivative of the derivative. By that, I mean the derivative of the first derivative is the second derivative. Now, since the first derivative is change in y over change in x, then the second derivative is the change in slope per change in x, okay? Since this is the first derivative, it's slope, then it would be change in slope over change in x. It's very important that you accept that fact as being true because we're going to use that in unveiling the second derivative test. We already know some notation for the second derivative. F double prime of x is 1, y double prime is 1. We're going to introduce a new one here, not that it's germane to this lesson, but we thought this would be a good time to introduce it. It's d squared y over dx squared. You heard it correctly. D squared y over dx squared. We'd like to share with you why the notation is such. This is for your information. Now, slope is dy over dx. We know that. And d is synonymous with change. That's why it's red. Change in y, d is change. Change in y over change in x. So change in slope, since dy dx is slope, would be change in slope d dy dx. And change in x, of course, is dx. Now we'll write this as d dy over dx for the numerator, and then dx, the denominator. Now, dividing by dx, remember, is the same thing as multiplying by 1 over dx, so that's what we're going to do here. D dy over dx times 1 over dx, which is d dy over dx times dx, which is dx squared. So this will be, since it's d dy, we'll write it as d squared y. And what we're doing here, and this is where I want to make it confuses students, this we write as dx squared. Now, this is not change in x squared. This is the quantity dx squared, okay? We write it like this, and let me share with you why. There's nothing else in mathematics that comes up that this will run counter to. And we have this thing in mathematics is we like to be exact, but never put down a mark in our work if it's not necessary. So there's nothing to confuse us with, because there is no such thing as d of x squared. It's dx quantity squared, but please make sure this is not a typo here. Of course, what you need to know is whenever you see this, it means second derivative. We're now going to look at some schematics, some visuals, to see if we can help you understand what's going on. And so when we do unveil the second derivative test, it's not such a shock to you. Hopefully it will make sense. We have in front of us a curve. It's a downward curve, okay? We've labeled points A, B, C, D, and E. Now, and then we've put arbitrary numbers here representing what could be the slope at this point. A does have the tangent lines of positive slope, so we're going to call it 2. B has a positive slope and it's less steep than A, so we'll call it 1 for lack of a better number. This does not mean that is truly what the slope is. Make sure you understand that, what it could be. This slope looks like it would be 0. This slope is negative. We'll call it -1/2. And this slope is also negative, and it's steeper than this one, so possibly -3 here. So these are just arbitrary, but that doesn't matter. What we're going to do is we're going to use this. C is a critical number, though. If the slope is 0, remember what the definition of a critical number is. It's a point on the graph where the first derivative, the slope of the tangent line, is 0. So that is a critical number. So let's consider, since we have these slopes here, why are they here? We want to see what the change in the slope is as you go around this graph. So when you go from A to B, this change in slope is 1 minus 2, which is -1. We're only interested in the fact that it's negative. When you go from B to C, it's 0 minus 1, which is -1, but we're interested in the fact that it's negative. Going from C to D, it's -1/2 minus 0, which is -1/2. Again, we're interested in the fact that it's negative. And going from D to E, it's -3 minus a -1/2, which is -3 plus 1/2, which is -5/2. But -5/2 does not interest us. What interests us is that it's 0. In other words, the change in slope in a graph that looks like this is negative. Okay. Now, we said in an earlier slide just a few minutes ago that the change in slope is the same thing as second derivative. So another way of saying this, rather than say the change in slope is negative, the second derivative is negative. Okay. Now, when the second derivative is negative, that means the graph is concave down. That's not going to be too important to us in this lesson, but we're putting it in here because we can use this later in the course. But we can use this fact that when your second derivative is negative, then the critical number is going to be a relative max. That's important. So when you have a graph that's shaped like this, its second derivative is negative and it has a relative max. That's what you want to take away from this visual. Next visual looks somewhat like, except the curve is inverted. Okay. So again, we've assigned slopes at A, B, C. This slope would be negative. We're saying, why not -3? This is a negative slope, the tangent line. Call it -2. Not again that they are exactly the slopes, but they could be. Slope here is 0, it looks like. Slope here is positive. Call it 1. And this one's steeper at E. Let's call it 4. Now, this indeed is a critical number because the slope of the tangent line here is 0. So by definition, critical number, this C is the critical number. Now, what's the change in slope as you go left to right? Well, it's -2 minus a -3, which is -2 plus 3, which is 1. We don't care that it's 1, but it's positive. 0 minus a -2 is 0 plus 2, which is 2, positive. 1 minus 0 is 1, positive. 4 minus 1 is 3, positive. So when you have a graph like this, the change in slope is positive. Again, change in slope is the second derivative. So the second derivative is positive. That means it's concave upward. Again, we'll make use of that later, which is written in that little orange colored box. But the fact that it has a lowest point, in other words, a relative min, is important. So if a graph is shaped like this, its second derivative is positive and it has a relative min. Okay. So here we have the second derivative test. And actually, if you've paid attention to what we just said, then this stands to be true. F of x is a function, and C is a critical number. If when you put C, the critical number, into the second derivative, if you get a positive answer, then it's a minimum, a relative minimum. If when you put C into the second derivative and you get a negative answer, then C is a relative maximum. That's based on what we just learned in the 2 previous slides. If when you put C into the second derivative and you get 0, then we don't get any information that's helpful to us as far as max mins, and we have to say the second derivative test fails. Second derivative test fails. Now we want to look at a couple of examples, 4 to be exact, and we're going to use the second derivative test to find whether the critical numbers are relative max or relative min. And some of these problems can be done with the first derivative test, but because this lesson is second derivative test, we're going to use the second derivative test. We'll amplify the fact that you have a choice later in this lesson, and again later as we go through sections aligned with this topic. So, first example. F of x is 1/3 x cubed minus 1/2 x squared minus 6x. We want to find the x coordinate of any relative max mins, and that's the direction of all 4 problems. So, repeat that every time. We need critical numbers. So we take the first derivative, and when we do, we get this, and with factors, set it equal to 0, and we get -2 and 3 are critical numbers, and there's nowhere the first derivative doesn't exist, so they are only critical numbers. So we take the second derivative, which is the derivative of this, which is 2x minus 1. We put in -2, and when we do, we get -5, which is less than 0. Based on the second derivative test, if the second derivative is negative, it's a max, relative max. Then we put in 3 and we get +5, that's greater than 0. That means x equals 3 is a relative min, and we are finished with that example. Example 2. F of x is minus x squared minus x minus 2. And again, we want to find the x coordinate of any relative max mins. So we'll take the first derivative, we get this. We set it equal to 0, we get this. It's my critical number. There's no way the first derivative doesn't exist. It's my only critical number. I take the second derivative. When I do, I get simply -2. -2 is less than 0. Now, what that tells me is, since it's negative, that means I'm only going to have a max. If I have a critical number, it's going to be a max. Okay, and so my only critical number is -1/2, so I will call it a max because the second derivative is always negative. You need to know that fact. Okay, that's important. Example 3. Again, a function, same directions. We'll take the first derivative. We do. We see we can factor to 4x. We do. We see we can factor this. We do. And then we find that 0, 1, and 2 are critical numbers, and there's nowhere the first derivative doesn't exist. So let's test our critical numbers. So we take the second derivative, which is the derivative of this, which is going to give us 12x squared. I'm sorry, if we take the second derivative of this thing, the derivative of this is going to be 12x squared, okay, minus 24x plus 8. I was looking at the wrong line there, excuse me. So the derivative of this is 12x squared, the derivative of this is -24x, and the derivative of this is 8. That's my second derivative. Now, let's put in our critical numbers. When we put in 0, we get 8. That's greater than 0, so it's a min. When I put in 1, I get -6. That's less than 0, so 1 is a max. And when I put in 2 into the second derivative, I get +8. And so that tells me that's greater than 0, so this is a min also. So we have a min, we have a max, and we have a min. That kind of makes sense in a way. In other words, if it's low point, high point, low point. Okay, now it didn't have to, it couldn't, you're not going to have 2 maxes in a row. In other words, you're not going to have min, max, max. That's for certain. Okay, so I want to keep that in mind. It's just knowledge is important. But anyway, I want to make sure that you see that this answer does indeed make sense. And let's wrap this up with problem number 4. Now, example 4 is x squared e to the x, same directions, find the x coordinate of any relative max min. So we'll take the first derivative now. In this problem, this one's a little harder. We've got to use the product rule. That's one of the reasons we're giving this. We don't want all the problems to seem too simple. Okay. So we have first times derivative second plus the second times derivative first, and that gives us this. we set this equal to 0, we factor, and we find that x could be 0, x could be -2. E to the x will never be 0. Okay, so my only critical numbers are -2 and 0. Okay, so they're my only two critical numbers. There's nowhere the first derivative doesn't exist, so these are indeed my critical numbers. Now I take the second derivative. Now this is where this problem gets a little sticky. I've got to take the derivative of this, which is a product rule, and the derivative of this, which is a product rule. And that's what we've done here. You can check us out here. And then we've combined like terms and factored. And so we end up with this. Okay, and now we're going to put -2 in the place of x. Now when I do, I'm going to get e to the -2. I'm going to get -2 squared, which is 4, and -2 times 4 is -8, and plus 2. And when I do the arithmetic here, I'm going to find that this thing is 2 over e squared, and this thing is going to obviously be 1 over e squared, and this is going to be 2. This is 6 minus 8, which is -2. So this is correct. -2 over e squared. And this will always, e squared is always positive. 2 is positive, negative sign in front. So this is going to always be negative, which means it's a max. Now, when we put in 0 into this thing, we get e to 0. And of course, 0 into this gives us just 2. So e to 0 is 1. This is 2. That's positive. So 0 is a min. And so we're through with this. Now, this problem was a little more difficult in finding the second derivative. Sometimes when you find the second derivative difficult to find, then you might want to revert to the first derivative test. There are times when the first derivative test is called for. There are times when the second derivative test is called for. And we don't want to go into every scenario because it's too many variables to cover here. But as you work problems, you will get acquainted to when to use which test, or you should. In other words, what we would like to emphasize is that you need to have in your toolbox the first derivative test, and you need to have in your toolbox the second derivative test. Both of them are vital tests in understanding what's trying to be covered in subsequent sections. And so this concludes this lesson.